Today we're going to talk about the graphs of complex numbers. So we're going to graph complex numbers in a special plane called the complex plane, and then we're going to convert between standard form and vector notation, and then we're going to look at what an argument and a modulus is of a complex number, and then we're going to find the magnitude and directions of vectors in the complex plane, and we'll go backwards too. We'll actually take a look at the magnitude and directions of vectors and find the complex number. So let's begin with the complex plane. So the complex plane is made of two axes. The first axis, which was originally your x-axis in the coordinate plane, that axis is a real number axis. And then your vertical axis is going to be your imaginary number axis. So let's say you wanted to graph the complex number 2 plus 3i. So 2 is the real number part, so you'll go 2, and then you'll go 3 up because that's the imaginary part. So this right here, 2 plus 3i, would be graphed at this part right there. Let's try another one, negative 3 plus 3i. So your real number part is negative 3, which means left 3. And then your imaginary part is 3, so you'll go up 3. Let's do one more, negative 6 minus 3i. So negative 6 left 6, and then down 3 for the negative 3. Alright, so we have a definition called a modulus. So a modulus is just thinking about the distance or the absolute value from the origin to the graph of the number on the complex plane. Okay, so the absolute value means distance, right? And so if we're thinking the absolute value of our complex number, that's the absolute value of a plus bi. Well, remember distance, it can be found using the distance formula. And it also, if this is our complex number here at a plus bi, then that means that this distance here is a, and this distance here is b. And we're trying to find this distance here, or an r, okay? Well, remember r can be found using Pythagorean theorem. That's just equal to a squared plus b squared equals r squared. So r, or our modulus, or the absolute value of our complex number, is found doing the square root of a squared plus b squared. So that's the formula for your modulus, right? The square root of a squared plus b squared, where a is the real number part and b is the imaginary part. Our next definition is called the argument. So the argument is the angle. So the modulus was the distance, and then the argument is going to be the angle. Okay, so it's the angle formed by the positive real axis. So you start at the positive real axis, and then you go all the way to the terminal ray that passes through that complex number. So that would be this right here, this angle. So this is your argument. So remember, to get an argument, this right here is a trig triangle, right? So you have theta, or your argument, and you're always given b, the imaginary part, and a, the real part. So you're given the opposite over the adjacent, which we know is tangent. So tangent of theta, or our argument, is equal to b, the imaginary part, over a, the real part. So if you want a formula for the argument, or for that theta, it's equal to the tan inverse b over a. Alright, let's practice some problems. Let's find the modulus of 3 plus 3i. So remember, the formula for modulus is the square root of a squared plus b squared, where a is the real part and b is the imaginary part. So we get the square root of 3 squared plus 3 squared. So 9 plus 9 is 18, so we get the square root of 18, which simplifies to 3 square roots of 2. So this is very important. Do not give a decimal right here. If you give a decimal, it will be wrong, okay? The square root of 18 simplifies to 3 square roots of 2, because the square root of 18 is the same as saying the square root of 9 times the square root of 2. And the square root of 9 is 3, so now you get 3 square roots of 2. So this is the most approximate that you can get. If you give a decimal, then it's not as accurate, and that's why we do not use decimals when there's a radical. We just simplify the radical and leave it like that. All right, so there's a definition for equal complex numbers. So complex numbers are equal if their moduli are equal, so their distance are equal, and then if their arguments or their angles differ by the multiples of 2 pi. Okay, so even though their real number parts can be different, the a and the b, the real and imaginary parts can be different, they can actually still be equal as long as their moduli are equal and the arguments differ by integrals of 2 pi. All right, so let's talk about something fun. It's going to be called, we're talking about vectors. So vectors is kind of the reason why we even study imaginary numbers and complex numbers. Like, this is the reason why we even consider looking at this and studying this in the first place. Vectors are the real world application of the complex number system. So a vector is just a complex number that is represented with direction and magnitude. So a vector is direction and magnitude, and so a vector can be represented by a complex number. So direction is like kind of like the angle. So 30 degrees northwest, or 30 degrees north, or 70 degrees south, like all that type of direction. And the magnitude, of course, is the distance, right? Which we've already discussed. And then oh yeah, so here it is. The magnitude, and another word for that is the norm, is just the absolute value, right, of the complex number. So remember, the absolute value is also called the modulus. So modulus, absolute value, magnitude, norm, they're all talking about the same thing, and that was that formula r equals the square root of a squared plus b squared. All right, so let's graph this vector, negative 2 plus 3i. So we start the same way when we're graphing a vector as we did when we were graphing a complex number. So you go left 2 and up 3, and then instead of just putting a point there for a complex number, so remember, this is a vector, so it has direction, so it has this, so we'll go ahead and draw a terminal ray, and then we're going to go ahead and place an arrow there to show that that's the direction that it is going, okay? And notice that it's only a half arrow, because with vectors, in order to tell the difference between a vector and a ray, a vector is only half an arrow. So vectors can be equal if they have the same magnitude in the same direction. All right, so we're going to work backwards. We're going to find the complex number that's associated with this vector, okay? So this vector has a theta of 5 pi over 6, and it has an r of 16. So we know that tangent of theta is equal to b over a, and b and a are the numbers that we need, because if we know what a is and b is, then we know the real part and the imaginary part of our complex number. So what we'll do is we'll start with saying that the tangent of 5 pi over 6, well, tangent of 5 pi over 6, you can use your trig card if you need to and look up 5 pi over 6, tangent of 5 pi over 6, and that will tell you that tangent of 5 pi over 6 is the same as saying negative 1 over the square root of 3. And that's equal to b over a, because tangent theta is equal to b over a. So if negative 1 over the square root of 3 is equal to b over a, I can solve for a. This is a proportion, so I can cross multiply. Negative 1 times a is equal to the square root of 3 times b. And then if I solve for a, I first have to divide both sides by negative 1, and that's how I get a is equal to negative square root of 3 times b. So here's a. And I've solved for a, but a is in terms of b. So I still actually haven't solved for a yet because I don't know what b is. However, I do know that my modulus is r equals the square root of a squared plus b squared. So instead of saying r is equal to the square root of a squared plus b squared, well, I know my r. I know that this right here, this magnitude is 16 equals the square root, and I know that a is the same as saying negative square root of 3 times b. So instead of saying a, I'm going to write the negative square root of 3 times b squared plus b squared. And so now I can simplify. the negative square root of 3 squared is just 3. So, and then b squared is b squared. So I've got 3b squared plus b squared. That gives me 4b squared. So if I solve this, I square both sides and then divide both sides by 4, and then I square root both sides. I find out that b is equal to 8. So if b is equal to 8, that means that a is equal to negative square root of 3 times 8, or negative 8 square roots of 3. So now I know what b is, and now I know what a is. So that means I can write my complex number. So my complex number is going to be negative 8. That should be negative 8 times, that's times the square root of 3, because that was my a value, plus 8i, because 8 is my imaginary part of my complex number. So the only thing is that we have to check that this complex number that we came up with is in the right quadrant. So this quadrant says that it should be in quadrant 2. So that means that my a should be negative and my b should be positive. So my a is negative and my b is positive, so this checks out. This is correct. All right, so a few reminders. Two vectors can have different locations and still be equal vectors. Okay, and then symbols for vectors include either a half arrow or a bold-faced font on a lowercase letter. So it kind of looks like this, right? So it has, this is a symbol for a vector with a little half arrow, okay? Or if you're typing, it will look like a bold letter U. That's also a symbol for a vector. And then the coordinates of a vector, instead of having the coordinates of a vector look like this, 2 minus 3i, we can also use angle brackets to go ahead and show those. So here is the complex number 2 minus 3i, and if we wanted to represent this in vector notation, we would use our angle brackets. We would put our a value, which is t, or 2, and then our b value, which is negative 3. All right, go ahead and try some problems.